Hello and welcome to a new Entagma tutorial. Today I want to talk about something that I found online on the site of Descriptiv, which is run by Dominik Kolb and Christoph Bader. And these guys really inspired me. I looked at everything they put online. And on Behance I found this, a project called Double Mesh. It's basically a program they created. And with this program you can create these beautiful structures. When I saw them for the very first time, I had no idea how to create them. But today, thanks to Houdini, I am able to do so. And I want to share with you how this works and how we can create something like this in Houdini. So this time we will do a classic Houdini setup, only a little wax here and there, but a lot of standard nodes. And I think this will be a fun project. So let's go directly to Houdini and begin. Before I start, let's minimize this area here with the parameters, because I can display the parameters by pressing the P key directly here in the network view. Now lay down into your node to hold our setup. I name it not double mesh, but dual mesh, just to have a slightly different name than what Descriptiv used, and dive inside. So what do we want to create? Let's first get rid of the file node and lay down a torus, because a torus is slightly more interesting than a sphere. Nice torus. Let's quickly jump back to what we tried to create. If we have a close look to this here, you see we have here in silver these triangles, and then in red we have pretty much, honeycomb n-gons. So how can we accomplish something like this? This is a quad structure. This is not what we need. We want the same object, but we want triangles only. So let's use the remesh node, because the remesh node creates a Delaunay triangulation on top of an input mesh, like so. That is looking quite good. To improve the quality of the Delaunay triangulation, we can up the iterations, say to 3. And the area of the individual triangles will be a little bit more even. And then we would want to create the second mesh, which is the honeycomb structure. And we can do so by computing the dual graph to this Delaunay triangulation. And fortunately in Houdini we have a standard node that directly does this off the shelf called divide. So lay down a divide node and connect it. And now check compute dual down here, and this is what you get. It's a Voronoi style remeshing of the whole object. If I now display both objects at the same time, you see this is basically the structure of what we are after. This is what we want to create. From here on, it's just making it pretty. Let's quickly put down two nulls. The first null is called Delaunay. And the second null will be Voronoi, just to organize things a little, like so. And by pressing C, bring up the colors and give this a nice color. So this mesh here is our Delaunay mesh. If we display it, you see it's the triangles, and this here is our Voronoi mesh. Little bit of organization, like so, and it's a little bit more organized. Eventually we want to bulge these individual edges. We want to bulge them outward or inwards and interweave both meshes. So what we need is not polygons like here, but we want every edge to be an individual primitive. How can we accomplish this? To do so we have a node in Houdini called convertLine. And what it does is it creates a primitive out of every edge of the mesh. And we can do this to both sides. If I display the primitive numbers, you see that we have a primitive for every edge, but we have the primitives share the points. So what we want is really a primitive for every edge that has unique points. So the next step is to unique the points. This can be accomplished by a facet node. Just connect the facet node. Let me quickly display the point numbers instead of the primitive numbers. And if I now go here and click unique points, you see now we have a lot more points, because now every single line has unique points as endpoints. We can look at this if we throw down a point jitter. And you see, if we do so, maybe scale it a little less, we have a bunch of individual lines using individual points as the endpoints. So far, so good. Let's get rid of the point jitter. So now for the bulging, we want the beginning and end point of every primitive to stay the same. Only the middle should bulge outwards or inwards. So what we need is more points. We want to divide every line in the middle to create another point in the middle that we can move outwards or inwards to create the bulging. And I decided to do so using the edge divide node. If I append this here and put a star here in the group to select everything, you see that every single edge is divided and one point is created in the middle, which is good. Now we can just take these points and move them outwards or inwards. The problem is, how can we select them? Well, one possibility is to create a group and to put this group before doing the edge divide. So let's go back and we group points and just group all points and call the group initials, because these are the initial points. Now, after the edge divide, what we can do is another group node, and this time we use group Boolean operation. So go to the combine tab of the group node, and here what I can say is my new group, let's call it midpoints, should be everything that is not in initials. Now it's selecting all the midpoints and only the midpoints. Perfect, because now we can just use these points to displace them. To actually displace them, I need two things. A point warp. Let's create one. Point warp and append it here. Call it displace. And normals, because we need a direction to displace the points along. And I can just use the normals that come standard with the object. It's just that I have to create them, actually. So I use a wrangle for this. Point wrangle. You can use a point sub too. And just type @n is @n. And this will create real normals out of the implicit ones. So here they are purple, and now they are blue, and we have normals on the mesh. And the good thing is that this edge divide will interpolate the normals. So all the midpoints, and we are caring about the midpoints, have normals too. So now let's dive inside the displace warp and lay down a displace by normal. Displace along normal node. And we can use the normal that comes in with the globals because we created it, and connect the displaced point to P. So now it's just about the amount, and I promote the amount parameter one level up. And now I can just move this slider. The whole mesh gets displaced along the normals. Turn off the normals. But we don't want the whole mesh to be displaced. We only want the points that we created here called midpoints. Remember, mid PNTS is the group. And if we put it here, the warp, mid, not mind, but midpoints. And now you see only the midpoints are displacing, which is very nice. Nice, but faceted. So let's make it round. And this can be done by converting everything to NURBS curves. So lay down a convert. And just convert everything we have here to NURBS curves. And suddenly you see everything is nice and round because the individual points now serve as control points to a NURBS curve. Eventually we want to put a polywire on top of this to give everything thickness, and the polywire does, as the name suggests, only work with polygons. So the next thing I will do is put down a convert again and immediately convert the NURBS back to polygons. Like so. And you see, by doing so, now we have polylines that are nice and smooth and round. And now append the polywire. Let's decrease the radius by a factor of 10 and quickly append a normal and maybe a color, just to have an indication that this is the first part of the mesh. Maybe even go back to the polywire and give it a little bit more divisions to make it round, like so. And this is the first part of our mesh. Now we can care about the second part of our mesh. The good thing is that the treatment for the second part of our mesh is exactly the same as the first part. So get rid of this old convert line, because we put this point wrangle in front of it on the left side, so we have to do the same on the right side, and just copy everything, put it over to the right side and connect the right side, and now you see it does exactly the same thing to the Voronoi remeshed structure. Give it a different color to be able to tell them apart, and lay down a merge to just merge the two together. And here you have the first iteration of our dual mesh, and it's looking quite good. It's just that all the individual lines are bulging outwards, and that is not what we want, because we want to interweave it. We want the blue stuff to go down when the red stuff comes out, and the other way around. Whenever the red goes in, the blue should come out. So let's care about this now. What we want to do is we want to create an attribute on the primitives called displace direction and make it 1 or -1 to be able to do different directions for individual lines. So every line should choose to go outwards or inwards, and this should vary across the whole mesh. How can we do that? Let's concentrate on the left side first by making this color node visible. What we want is we want a wrangle, but this time we want a primitive wrangle because we want to define the attribute per primitive. And I want to put this wrangle before the edge divide. This is because we want to do it per primitive. It probably works after the edge divide too, but because the edge divide is only adding points and not inserting primitives, but I want the points to interpolate the attribute, and that's why I put it before. Like so. So call this displace direction. And what we want to do here is we want to find a value that is unique to every single line, and that tells the line if it should go outwards or inwards. And I will create a new attribute called disp_dir. It's a float, and it should be -1 or 1. So I will base it upon the primnum. And I will just do a modulo by 2, such that every single primitive gets a different value. If we display the geometry spreadsheet, go to primitives, you see here the displace direction is either 0 or 1 in an alternating fashion because it's based on the primnum. And I want to just remap it to be -1 or 1. So put all of this into parentheses, like so, and just multiply by 2. Now it is between 0 and 2, parentheses again, and now just subtract 1. And this yields the result we are after, so -1 or 1 as an attribute. Now let's use the new attribute, but remember we want to use it down in the displays. But the displace is displacing points, and our attribute is a primitive attribute. So what we want to do is we want to promote it to points. Attribute promote, and disp dir used to be a primitive attribute, now it should be a point attribute. Let's quickly check if this worked. So yeah, here it's disp dir, and now we have it here on the points. All the points that are belonging to one primitive just inherit the attributes from the primitive. And the edge divide then interprets these attributes. Now go to the displays. It's a little bit smaller again, and let's bring it in. So create a bind and bring in disp dir, displace direction. And what we want to do now is, instead of promoting this amount, let's create a typical parameter node and then a multiply, because we want to vary this amount by the displace direction. And use this as the new amount, display the color, and you see now we have every individual line choosing going inwards or outwards. So what's left is to make the right side correspond to what the left side does. If we display both, you see it's not working at the moment because the blue stuff is bulging outwards everywhere. We have to tell the blue lines somehow that they should do exactly the opposite of their red counterparts. So here, when a blue line crosses a red line, it should choose the opposite value of what the red line does. How can we do this? We have to somehow find a correspondence, but this correspondence is not so easy to find because there is no numerical correspondence between the two. We have no primitive numbers we can use because it's really two completely different meshes. So we have to think about how to do this, actually. If we display the stuff before the displays and we display the other side before the displays too, what we see is what we have is a spatial correspondence. So here it's a little hard to see, but you have the lines that are corresponding. They are sharing pretty much the same space here, and we can use this property to find the right value. And we will do so by first putting down a point wrangle again, but this time on the right side before the displays. And here we want to check for the nearest point. We want to find the nearest point of all the points on the right side on the geometry of the left side. So what we want to do is we want to bring in this geometry before the displays into this check near point. And now we write a little expression. We create a new attribute and we call it near point and PNT. And this should be the nearest point in geometry 1 that is nearest to the current position of the current point. So what this gives us is, if we look at the geometry spreadsheet, is we have a new nearest point variable. It's a float at the moment, which is not right. Let's make it an integer, which is telling us the index, the ID number of the nearest point on the left side geometry. So now we have a correspondence between the points, and we can use this to fetch the correct displacement value. But to fetch a value, we first have to create a value. So let's go to the left side, to the displays, and create a bind export. And export disp weight. And we will just export this multiplication here, because this is the amount of displacement and the direction of displacement multiplied together. And this weight will be used on the other side. So now let's go up and go to the displays node on the right side, but bring in to the second input here the output of the displays on the left side, including this attribute. So we created disp weight. Now we have disp weight here. Disp weight. You see? And we want to use it on this side. Now let's finish this off, create a bind, and let's bring in the NPNT near point parameter, which is an integer that we created earlier. This is the nearest point on the geometry that comes in on input 2. So now let's import a point attribute from this second input. And this attribute is disp weight. And it's a float. And we want to look up this attribute on this point here. So this is a disp weight that is used on the corresponding primitives on the left side. Now what we want to do is we want to invert the value. So let's create a multiplication by a constant, multiply by constant. And just multiply everything by -1. Now that we have the inverse value, we can just put this into amount, and there you have it. It's displacing. Now let's check if the merge is giving us the correct result, and look at what we have. Now we have the dual mesh where all the individual edges are interweaved. As a finishing touch, select the 2 polywires and make the top polywire a little thicker. The other one too. And let's display this all as just smooth shaded. And here you have the dual mesh. That's the principle. That's how I built this object. What you saw in the demo picture is a little bit more involved, because I created different noise functions to vary the size of the polygons and the thickness of the individual wires and stuff. I will upload the demo file for you. So this is a principal thing, how it works, and all the bells and whistles are in the demo file. So if you want to recreate exactly what you have seen, just download the demo file and have a look. Thanks so much, and I hope you visit us again next time.